introduction. Yeah, so I'm really delighted to be here. Again, since you're all here and we're a relatively small group, if you have questions along the way, feel free to interrupt. If I don't notice the chat, just feel free to even unmute and speak. But today I'm going to be talking about an overview of some of our recent research looking at, again, as the title says, kind of how do we kind of enhance kind of human AI collaboration, in particular with kind of when people are trying to make complex decisions with data. My kind of main research area is data visualization. So as Augusto mentioned, I co-direct the data interaction group with Dominic Moritz, which is a lab at CMU in Pittsburgh, where again, if any of this research that I talk about today sounds interesting to you, feel free to go to dig.cmu.edu to kind of learn more, see the papers and videos and even demos too. But with that said, let me just motivate our work a little bit at a high level. So again, maybe some of you can relate to this, but for a lot of people, when we're trying to do our jobs, we're kind of surrounded by data, opportunities, new data exists that ever existed before. And for many of us, we're just not really sure exactly how to leverage it. And we want to help maybe incorporate all this data so we can make better decisions, but then we just don't know how to do it. And a lot of people just give up, right? And so what our research group really tries to do is give people kind of these superpowers to kind of find the patterns, leverage our innate perceptual abilities to help us find the patterns in these data. But then, of course, we don't want to accidentally turn people into supervillains by giving them kind of, patterns aren't really there or simplifications of complex things that don't really exist, right? So we want to be very careful that we're actually showing information that will help people and not make them naive and actually do things they shouldn't do. So it's this kind of balance between the two, right? And so nonetheless, what we really try to do is we try to build tools to help people kind of incorporate data when they're trying to make important decisions. Um, but um, but of course, data is just one part of this kind of decision-making process. And so, if we kind of, think about how people make decisions right now, and maybe each of you on the call can relate to this too. Oftentimes, if you're presented with making a decision, oftentimes you're going to rely on kind of your own expertise, your experience, or your education to really make that decision. So, for example, if you were a doctor, if you're treating a patient, you might notice some symptoms, check out some lab tests, and then lean towards a particular diagnosis, right? And that might lead you to, make a decision of go forward with this treatment or not, right? When we talk about human AI decision making, this is now a chance where, you can get some input from an AI to kind of give you guidance of whether you should or you shouldn't do what you think you're going to do, right? And so the question though is how does this actually affect the decision-making process? Typically, oftentimes when people are trying to measure how AI affects this, they'll do some common measurements like self-reliance, which is like, do they stick to their correct insights in light of the AI? Or do they under rely on the AI and perform worse if they follow the advice? Do they over rely on the AI? And so these measurements are really interesting. And in fact, we have some work published at CCW recently that kind of looks at the impact of these things. But I think we need to go a lot deeper because it's not really just the presence or absence of AI, but really how the behaviors of AI and how that AI is described or presented that can really impact how a decision making in some sense, right? And so that's what we're going to really talking about today is again, if the AI gives you advice and you change your mind, how can we understand what's really at fault there? Not at fault, but contributed to that. And this is particularly because, AI behaviors can really sometimes be inconsistent and erratic, right? So how can we really understand the impact of AI on decision making if we don't really have a clear understanding of how AI behaves? And so I think we need to step back and think about how we can consistently monitor AI behaviors. So I'll chat a little bit about some work that we published at Chi a year and a half ago or so, which is Zeno, which is kind of a framework and visualization tool for making sense out of AI behaviors. But I guess a spoiler alert, behaviors are often weird when data is weird. So then I figured we also kind of needed better tools for developers to kind of monitor weird data as well. And so I'll kind of talk about a tool called AutoProfiler that will help speed data scientists up to kind of understand what data is before they feed it into any AI algorithms. Um, and then finally, the way that AI presents itself to the user also has a big impact on whether or not the decision maker might agree to it. So this needs to be a component of these studies too. You might see, if you're familiar with this kind of concept of explainability, but basically you can see a lot of papers in the academic space that say explanations always help or explanations always hurt. And that's because there's lots of different ways of communicating what AI is doing. So I'll present one use case of such a deployment of an AI decision support tool in the intensive care unit of kind of a major research hospital. Um, and then I have a feeling we're going to run out of time, but if not, I can maybe also ramble on a bit about how the preciseness of explanations can have a huge impact on reliance as well. Um, and those faces that you see below each project are really the PhD students that kind of led each of these different threads of work: Alex, Will, Venkat, and Caitlin. And they're, of course, the real reasons why I'm able to talk here about these things that hopefully you'll think are cool and worthwhile. Alex recently graduated, but Will, Venkat, and Caitlin are all PhD students with me in the HCII at CMU. Okay. Um, so I'll get deep into these for a bit. Let me just start off with some high-level motivation. And I think probably, given that you're taking this human AI interaction module, this probably doesn't need too much motivation here, but basically, we've really seen this broad proliferation of AI over the past decade, right? In the 2010s, we saw this deep learning shift that really unlocked unstructured input data. So things like, ImageNet model, all this way of like being able to do self-driving cars, maybe automatically access medical imaging, doing machine translation at really high quality. Um, and so really being able to handle this unstructured input data, whether it's text or videos or images, and doing something with it, and capabilities that we weren't able to do before then, right? And now we're kind of in this kind of generative AI era, if you will, the 2020s, where now we also have the capability of generating lots of unstructured output data, right? We can easily generate images, videos, and text using generative AI. And so now we get all this data out of it that is also really hard to understand. Is it doing what we want, right? Um, and so this is kind of where we are right now. Um, but this proliferation really means that many more people are interacting with AI systems, whether it's, some assistance while we're driving a car, or doctors using AI diagnosis tools, or even authors like you are using ChatGPT to help write some essays, right? And basically, as users interact with AI systems, they typically develop mental models of how they behave. This really happens with any complex system that we work with. And of course, our mental model really informs how we interact with AI. So we kind of start learning, when should I trust this? Maybe how do I write my prompts to get what I want? All these different types of things that we kind of learn as we get more and more experience with AI. Um, um, but of course, the people that spend even the most time developing mental models of AI are the engineers probably creating these AI systems. And they can maybe sometimes use this information really to decide how to update a model. So for example, if you've ever had some experience taking an introduction to machine learning class, or even just kind of learned about it a little bit, typically the way we would learn how good a machine learning model would basically be to calculate some aggregate metrics, so like performance metric on it. So basically, have hold out some, train it on a bunch of data, hold out some data as your test set, and then you see how well it performs on that test set, right? That's typically how machine learning models are evaluated at scale. However, what I'm hopefully, if you have one takeaway from this talk today, is that really that, you know, as we've did this shift to deep learning, researchers and practitioners have really found that aggregate metrics are really insufficient for developing adequate mental models. And I think this is primarily for two reasons. Number one, it's really important to understand model performance for different types of inputs. So, for example, maybe you've heard of this particular example before, but there was a famous research paper that came out a few years ago called Gender Shades. And basically, they were kind of looking at public APIs from various companies that would kind of had image classification models. In particular, these models were trying to automatically calculate gender from images, which has maybe why they're doing that unclear, but nonetheless, it was a feature on deployed models that you could pay for to use via APIs. And some researchers said, hey, let's just like see how well this model works for different subgroups of people. And here the subgroups are quite broad, males and females with either lighter skin or darker skin. And as you can maybe see, and if you squint on this model, you can really see that certain groups, the performance is much, much less than other groups. So if you look at, the model on the third row, you can kind of see that this model performed much worse than for females with darker skin than males with lighter skin, right? You can get there's actually a 35% accuracy difference across this, right? And so again, if you look at the overall accuracy on all the images, it's pretty high. But if you start to if you start breaking this down into smaller groups, you see that sometimes performance can suffer. So that was number one. And number two was also people care about different measures of quality too. It's not all just about accuracy right now. And this becomes even more apparent with generative AI. So, for example, if you have ChatGPT make some text for you, how are you going to say if it's good or not, right? There's like all these different dimensions: how fluent it is, how truthful it is the style do you like, how coherent is it? All these different type of things that are kind of fuzzy to measure. And so you might need to really take into consideration a bunch of different measurements. Um, and so Alex Cabrera, one of the PhD students that I advised and recently graduated, really identified a key concept where he combined these ideas and kind of coined them as a model behavior. This is basically, a quantifiable pattern output for a semantically set of pair of inputs. And so more simply, this is basically just like a metric calculated in a subgroup of data, just like we were able to calculate performance on different people, genders, and skin tones, for example. That's one subgroup, an example of a metric on a subgroup. So here's some other examples, like, we might know that this AI is not working very well for people over the age of 60, or we have this image captioning model that can take images and write a text caption, and it for some reason always confuses climbing and skiing 50% of the time. Or maybe you're using, some help for helping you write code, and it's giving you, deprecated syntax in about 10% of code output. So basically, code that doesn't work anymore because it's deprecated. And so, anyways, those are just kind of examples of some high-level model behaviors. And Alex's dissertation work really suggested that mental models are really best represented by a set of behaviors. So wouldn't it be nice to know the behaviors of our models when we're making our decisions? And so again, they would really need to be very task specific and the right level of granularity to be useful. So for example, if you're a doctor trying to use AI to help you understand an image, and if it tells you that, hey, the model doesn't work so well when the tissue is very dense, then that might, lead you to believe, okay, you know what? I need to pay a little bit of extra attention whenever there's dense tissue results. Or again, if I'm talking about a developer that's maybe trying to train a model to do machine translation, and for some reason, the model tells us, you know what? This is not going to work if you kind of use a low resource language, right? You're going to get some weird, our model wasn't trained on this language, therefore the results you're going to get are probably not going to be great. Then you might know, okay, well, you know what? If I really want to do this task, I need to collect more data from these low resource languages to do that, right? So again, the idea here is that can we give people kind of task specific and useful information about the subgroups of where it performs well or where it doesn't perform well to help guide them to make better decisions with AI. So our hypothesis was really that these behaviors that I'm calling are kind of a good description of mental models and how AI developers actually kind of do it. But we really ran two interview studies to really understand how AI practitioners actually do this work. We first interviewed a bunch of people at Apple, technical and non-technical stakeholders, really trying to just understand, okay, what are the tools and interfaces that you use when you're building AI or ML support? And then we kind of expanded that with some other evaluation interviews where we talked to 18 different AI practitioners across different types of companies, everywhere from startups to big corporations, and really tried to understand what is their process for kind of evaluating AI or ML systems. And basically, it was clear that AI development really does revolve around these behaviors. All of the participants actually looked at specific behaviors during the development. Even 10 of them, about a third of them, actually created test sets for evaluating specific behaviors. So again, they'd actually kind of, so for example, one of the participants had, basically a set of text inputs with common typos. They'd pair their valid outputs, and they would make sure before they would release the model that it kind of worked for all these typos, for example. That's just one example. But the interesting thing here was that none really used any sort of standard framework for behavioral evaluation. It was kind of done ad hoc or not at all. So for example, one participant said, I really wanted to do some deeper testing, but we don't really do anything like that because there's not really an easy way to set up a system like that. So our main takeaway was, again, practitioners try to take a behavior-driven approach in practice, but really the tooling isn't there. And so that's led what Alex to lead this project called Zeno, which again is this kind of general purpose behavioral evaluation framework. I'll give you a demo in just a second. Basically, the idea is that you can really, it works for any type of data, So you can feed in any type of data, any type of model, and it will kind of let you kind of create slices of subgroups and kind of let you to validate your hypotheses as well. And so maybe I'll just kind of bravely try to pivot to a demo. We'll see if this works live. And if not, I can resort to a video. But I'm going to just go to, and if any of you want to check this out later, you can go to zenoml.com. And again, this is an open source tool that you can use to browse machine learning models. I'm just going to click explore projects and we'll choose one together. And again, hopefully it works. It's loading a little slow, but I'll choose one about audio transcriptions, even though maybe that's not the most visual one. But let me give you a little overview here. So this one was actually run by some people trying to evaluate how well OpenAI's Whisper model works. So Whisper is, again, it takes audio to text. So you can kind of see in this example, this is a corpus of data loaded in using the OpenAI model to basically see how well it can transcribe people's voices with different accents, with different places across the world that learned English at different levels. So basically, what it's trying to do is it's trying to understand how well the model performs for a diverse group of users. And so if I maybe play this.
Please call Stella. Ask her to bring these things with her from the store. 6 spoon.
So basically, it's a paragraph that they have to read, and they've collected a lot. The researchers behind collecting this data set got lots of different people that learned English at different ages and had to read this diagram. We kind of want to see when this model performs well, because right now the model performs really well. You can kind of see here where I'm mousing over it, and maybe it's a little small on the screen, but basically the average word error rate is 0.19, which means it gets about 20% of the words wrong, but that also means it gets about 80% of the words right. And this is a pretty big accomplishment for because most of these are non-native English speakers, so from all around the world. So you might think, oh wow, OpenAI is doing great. This is a wonderful thing. But what we wanted to do with this tool is to understand, are there certain subgroups that this model performs well, better on, or less than? And that's where something like Zeno can do. I'm actually going to just change this number here just so we can see these differences a little bit clearer. But what I can basically do is I can start on the left-hand side, start scrolling down some of these attributes. Now, this might be a little bit hard to see, but you might be able to tell that things get a little bit more darker purple as age increases. And Zoom sometimes compresses that so you can't see that clarity very well. But anyways, you can maybe see that it's getting a little darker. So what this means that the model seems to perform a little bit well on older people. So for example, a little less well on older people. So if I just highlight this group, for example, we can see, okay, the average word error rate goes up a little bit, not too much, but a little bit. So if they're over the age of 50, they're not going to do as well with this model. But where it gets even darker is if I look at the age of onset of when they learned English. So for example, here, if we look at people that learned English after the age of 34, now here, the average word rate is 0.47. It's getting almost half the words wrong. And so you can maybe, even if I start to scroll here, you can start, seeing here that instead of saying, please call Stella, it's saying, please cause later. So getting a lot of words, 6 spoons of fresh no peas, not 6 spoons, right? So it's making a lot of mistakes. For example, we could even maybe, I've never done this before, but maybe I could even say, okay, if I just look for all the people that were in this data from Spain, or let's even do Portugal, sorry, Portugal. Let's see if there is some in here. Maybe we don't have, oh, sorry, set. We can see that, okay, it actually does really well in people from Portugal here. So the model is actually performing quite well, 0.14. We only have 4 speakers in this case, but all of them are doing quite well, for example. But if I, but maybe if I compared it to a neighboring country like Spain, we could maybe see that here the average word error rate is actually much higher than average, 0.26. And so we could maybe start breaking down why that is. And we could even focus on the ones that are getting a lot of mistakes. And we can kind of see that for some of these people, it doesn't even think that what the input is English, right? So I'll play this little cue.
Please call Stella. Ask her to bring.
And for some reason, OpenAI returns what looks like Greek to me. I'm not 100% sure, but again, it did really bad. So you can see there's some subgroups that it's doing really poorly on. So again, I don't want to go too deep in this analysis of OpenAI Whisper, but nonetheless, I'm hopefully giving you some intuition that if you slice and dice your data, what seems like it works really well on some things, it might perform poorly for certain subgroups. We could then start to learn why it's performing and maybe even, again, try to figure out a mitigation strategy. So again, you can try this on your own. Go to zenoml.com if you want. But with that, maybe I'll jump back to the slides just so we have enough time to cover all the projects. So again, I won't say much about this, but basically we tried to make this really easy for developers typically machine learning developers don't like building kind of user interfaces. So we basically gave them an API where they could generate a UI automatically if they just added a few lines of code in their kind of code and basically made them this kind of way to kind of allow them to define evaluation building blocks that made sense for whatever they're doing. And then again, what you just saw a demo of was the exploration UI where they could really explore the behaviors of these tools and then even work with, creating reports for other types of stakeholders, right? So even developers don't make the final decisions often when a model ships or not. So could we also give kind of other types of stakeholders the ability to kind of compare performance across models and data slices and so on and so forth. So um, again, we've done a lot of case studies with Zeno, everything from, again, working with, doctors trying to make sensitive medical images to understanding how text-to-image generation systems work, like kind of Stable Diffusion or DALL-E, and trying to kind of find patterns about where things work and where don't things work too. But yeah, but right now we've had about 500 users, about 2,500 projects, and about 15,000 models that have been kind of analyze using Zeno. And so again, if this is something that kind of interests you, feel free to check that out in more detail. But again, I think hopefully here the takeaway message is that looking at giving tools to kind of help people figure out smaller behaviors models is really, really helpful to know whether they should trust it or not. And we learned a lot about how people were able to make decisions about their models, about, is it actually behaving as they expect or not. So I guess I'll pause briefly if anyone has any questions, but what I'm going to kind of talk about next is really about, okay, so let's say you use something with Zeno, you find something that's not doing well, what do you do? And so a common approach might be, well, okay, let's just train the model in different ways, use a different architecture. Let's see what the latest and greatest thing that's come out of a new model that's come out and just hope for the best. And of course, you could do that, and Zeno would help you compare models on slices and see which ones might win out. But sometimes nothing's going to win for a certain slice, right? And that might be just because there's like an underlying issue with the data. Maybe there's not enough data, there's bad training data. That gets me back to my original slide, where really, again, understanding the data that feeds into the behaviors is a really important aspect. So I'll pivot now into some work by PhD student Will Epperson, who again, kind of likes to say that kind of, one of the major bottlenecks for AI is not only compute, but rather the kind of time and attention of model developers. So, of course, we hear of, all these big organizations like OpenAI and Google. They have all these GPUs. They can spend countless hours training LLMs and whatnot, but they don't necessarily have countless hours for their developers to kind of explore and understand the data. In fact, there was even a survey a few years ago called the State of Data Science Survey, and basically really kind of produced some evidence nicely that said really that, data quality issues are often undervalued when people are building models. Data scientists self-report spending almost half their time just cleaning data and looking at it. And with larger and more data sources, building data understanding has really become slow and repetitive. And that's really because the kind of current analysis requires a lot of manual work at each step. So for example, a user might start with a question hypothesis. So they have to then kind of, then they want to figure out how to query the data for that, and then they have to look at the road, right? So in practice, this means they might have to write code for data exploration, then they have to write code for filtering and transformation, and then they have to then write some code to kind of visualize and verify the results. And as you might imagine, this takes up a lot of time, and it's sometimes painful to do. And so what our idea working with Will was really to figure out, okay, how can we actually kind of support this live and on the fly? So basically give people the tools to kind of automatically profile their data as they're doing the tasks that they normally do. And so we kind of called this continuous data profiling analysis, where basically as people are doing things with data, it kind of gives them this kind of automatic visualizations that kind of allow them to kind of verify the result. So we really tried to kind of make this feedback loop as fast as possible by giving kind of automatic data profiles. And our hope was that this would kind of lead to fewer errors and also a better understanding of the data itself, which was the tool. So again, we have this open source tool, AutoProfiler. I'll give a demo of it in just a second. But again, basically the idea is as a data scientist is about to use code, about to shove it into a model or whatever else they're going to do with it, we could basically give them a profile of it for free. live update whenever the data changes, and then even give them tools to kind of export the code to notebooks, whatever, if they want to do some sort of follow-up analysis or customization and so on and so forth. Let me try another live demo if I can. I'm just showing this in action just to give you some intuition of how it works. I think I have it open in maybe another browser already. Here we go. So for those of you that are data scientists, this might look familiar. If not, no worries. This is just called a Jupyter notebook. It's really a common way that a lot of data scientists organize their code. This is some simple code here. And basically the idea is that each of these cells is a line of code that does something. And this might be the way that someone, basically loads in a library, reads in some data, and then starts doing some transformation, like they're filtering it to kind of do it. So let me show you how AutoProfiler might help this process. So basically, it's a little plugin for this that you kind of click this button, and what you see, it kind of appears on the left-hand or right-hand side. And as I run a line of code, so on this third line here, I'm actually going to read in some data. So I'm going to call this read CSV of where my data is stored. And what I'm going to get is you'll see here on the left-hand side, automatically after I read in that data, I get some overview of what this data looks like. So we can kind of see I have about 20 different columns here in this particular data set. We just loaded in some data about housing prices in the Bay Area. So just kind of how much rent costs and what are the features of them. So basically how many beds, how many bathrooms, how many square, how big the apartments are or houses are, what neighborhood they're in, so on and so forth. And what this profile tries to do, and hopefully it's not too small on your screen, is it tries to give you a little bit overview of what's happening there. So for example, we can kind of see, if I want to see what are the most common neighborhoods in this data set, we could see that Santa Rosa, Santa Cruz are kind of the big neighborhoods in here. And it even tells us, what percentage of the data they kind of occupy and so on and so forth. If we look at the number of baths, we can kind of see a distribution of how many bathrooms are in each property. But we can also even see here that about 80% of these values are actually null, which means that for a lot of the listings we have, we don't know how many bathrooms are there. And so if you were going to train a model that was going to predict, based on the number of bathrooms, how much this property would be, it probably wouldn't perform so well because so much data is missing, right? And so we try to kind of point out this information there and so on and so forth. You might even say, okay, I'm looking at the date and I want to see the distribution of the date. And you realize, oh, wait, actually, this thing is not in date format, for example. It just thinks our model or our system thinks it's just a number. And so we could even write some code to convert that, which I'm doing in line 4. And you can see once I do that, you can kind of see now we get a nice temporal visualization of what the data is. And we could say, okay, let's actually look at, all the data around these dates, for example. And then finally, what we could also do is let's say, okay, this is interesting. I get an overview of things going on. I can kind of see what the most common things are about these attributes like price and look at the distribution here. But maybe I'm like, okay, I really want to focus on those expensive rents. So what I could then do is I could write another line of code saying, okay, I want all the places that cost more than $5,000 a month. I could do that here, and then suddenly a new data frame will appear on the left-hand side too, and we could start comparing and contrasting these and start thinking about, the neighborhoods in this one look a little different than the other one, and so on and so forth. So again, here, the main intuition is really, it's kind of painful after every time we do some data transformation to kind of inspect the data and make sure it actually behaved as we expected. With this type of tooling, you kind of can get that functionality for free. And so our hope is that if we let this happen easier, people can spot their mistakes more easily, and then we'll kind of lessen the chance of things going wrong when they actually feed these data sets, blindly into models to train on. So again, it's a little simple example there, but hopefully gives you a little taste for how that tool works. And again, this is kind of open source and you could play with it if you happen to work in these types of environments. But again, of course, we wanted to make sure it worked. So we kind of did a user study with both, a shorter lab study with just 16 people to really understand how AutoProfiler worked, and then kind of a longer study with, I'll talk about that in just a second. But basically, this user study was basically like, okay, we got 16 experienced data scientist users, and we basically gave them a task, we gave them a data set. We said, okay, you got to produce a report for a colleague before they use it for the model. Tell them everything that you think is good and bad about this data. And we kind of gave them 2 different conditions. One was AutoProfiler, which I just showed you. We called that a live. Then we also gave them a dead condition, the static profiler, we called it, which was a baseline we built. It was basically similar to functionality, except that instead of automatically appearing on the right-hand side whenever they made a new thing, they had instantiated themselves when they were wanting to see something, which is kind of the current common practice of how that works. And I'll just go through some highlights the high level, but basically, actually, whether it was alive or dead, both systems kind of led to a similar number of insights discovered. Um, but uh, but live profilers clearly made the verification much easier. So, for example, one said, it was nice to see that when I kind of changed all the text to uppercasing, I can see, oh, that worked. And when I dropped duplicates, I could just look and see, oh, that worked. And they like that a lot too. Across both systems, kind of, 91% discovered insights that came from the tool rather than users writing the codes themselves, and so they said, one user said, yeah, I might have known to look for this particular error, but it would have taken me a lot longer to remember how to do it with the syntax, right? And then finally, three, we also saw that AutoProfiler really helped these exports. I forgot to demo that in the demo, but basically the idea is that if you find a visualization that you like, for example, let's say you really think that this chart of bathrooms is really telling a good story, you could export this to the code, and then it would kind of live in your code forever. So you could kind of, again, see that here too. And so this was kind of uh, help people even, they were able to keep track of what they were doing, but sometimes they would even just learn from this, right? There was an educational perspective that, I didn't really expect to know how to do that. And I could just like export the standard deviation and I could see these points. And then, when I saw there was a code to do that, I kind of learned that. So it had that kind of extra benefit of actually teaching people some best practices of how to generate these visualizations too. Then we also had, scientists using this tool at a national laboratory in the United States, kind of used it for 3 months and kind of really, they started kind of use it in their day-to-day work while they were kind of doing scientific experiments. And it really helped them kind of reach a lot of serendipitous discoveries that might have otherwise gone unnoticed. Um, and I'll just say that Will's kind of current work kind of builds upon this by really building this new type of profiler for text. So he's building this new system called Texture, which is kind of still under submission, but basically it's a way of how we can kind of do similar types of things by automatically creating profiles for large text data sets. So again, before the original system I talked about was more for like tables of data. Now text is even harder to deal with because it doesn't have structure. So how do you do that? So really figuring out interesting ways to create profiles of text, and some of it even kind of deriving new structure from LLMs. But I won't get too deep in there today. But happy to chat more about that if anyone has questions. Okay. So I talked about behaviors. I talked about how we can better looking at behaviors of AI models, talking about maybe getting a better look at data. The last thing maybe I'll chat about today is really focusing on the presentation aspect. And so this is really, again, about how can we actually present what the AI is doing so people can kind of make sense out of it. And so I'll go deep on one particular example here, a work led by another PhD student in my lab, Venkat, who has been working in the area of AI in healthcare. AI powered systems in healthcare have really been designed to help clinicians make diagnoses, retrieve relevant information from health records, make prognoses about patient survival and mortality, and lots and lots and lots of other applications. Um, uh, but a common theme across these use cases is that often they rely on kind of the presence of a gold standard for evaluation, which is typically maybe the decision that a good team of clinicians would take. And so the algorithm just really needs to replicate what those clinicians would do, and that would then maybe help them streamline time-consuming and expensive tasks. But what about cases when the best decision isn't as clear cut? So, for example, in this work, we studied treatment recommendations, and in particular, treatments that are chosen multiple times over a patient's trajectory. It's kind of more difficult to determine what the best decision is in these cases because maybe the effects of future treatment choices can really confound the effects that we measure for past ones. Now, we have techniques to maybe build statistical models to try to detangle these effects, but to evaluate these models, we often need to deploy them, which could be dangerous in a clinical setting, right? So how can we assess whether treatment recommendations are really, really helping patients or not? And so we studied this problem in the context of sepsis, which is a life-threatening condition that's often treated in the intensive care units of hospitals. And so what does it mean to have sepsis? Essentially, sepsis occurs when your body's response to an infection, such as, for example, the coronavirus, right, causes damage to vital organs. Sepsis is really currently one of the major causes of death in hospitals. Um, but most of the research on AI for sepsis has really focused on diagnosing or predicting patients with sepsis. Um, but once patients are diagnosed, there's another set of challenges around treatment. Clinicians typically manage sepsis using a variety of treatments like antibiotics, IV fluids, and drugs called vasopressors. But like many diseases that can present in diverse ways across patients, it's often kind of infeasible to conduct enough randomized controlled trials to kind of determine the best type and the timing of treatments. So treatment decisions for sepsis are often complicated, uncertain, and highly variable between providers. So now, as I mentioned, machine learning approaches for treatment recommendation have been shown to lower mortality when tested on um, so I should say that machine learning approaches have been shown to lower mortality when tested on historical data, but to our knowledge, they've never really been tested prospectively, like in a real setting, like in a prospective setting with real clinicians. So that really led us to kind of the main research question of our study, which was, again, how do clinicians actually interact with and decide whether to rely on AI-generated treatment recommendations? And we address this question by building a visual interface and then conducting a think aloud study, decision-making study, which I'll kind of go into next. And again, sepsis is a really a big public health concern. So this is really important. If we start deploying AI tools to help doctors, what are they going to do with that information? The basis of our study was an algorithm called the AI Clinician, which was developed and published in Nature a few years ago. This algorithm basically uses this kind of mimic open data set to optimize over a finite set of patient states and treatment actions to basically minimize the expected mortality. I'm not going to go into more detail here about the algorithm, but happy to talk later about the challenge using reinforcement learning in a clinical setting if you're curious. But basically what we did was that before we could show that AI clinician to a human clinician, we actually first had to visualize patient cases and kind of understand what the model was recommending for them. So we developed this interface. I think we called it the AI Clinician Explorer uncreatively. This tool, which you could try for yourself at link if you want, really kind of allows clinicians to kind of browse through these patients at different states throughout when they're in the ICU and how the AI would have predicted what for them to do or not. So this kind of was an interactive tool that we had to build just so even our clinical colleagues could understand what is this algorithm doing and find the patients that would be kind of reasonable to put in our study that would kind of have different characteristics. And so then what we did was after we kind of built this tool, that tool kind of served as a stimuli for a study that we designed it to answer our research question, which again was a think aloud study with 24 practicing clinicians. So 15 kind of full attending doctors, 6 ABPs, and 3 fellows, kind of trainees. And basically what we did was we showed participants 4 variants of the interface that I just showed, with each variant kind of paired with one of 4 patient vignettes in a random order. So you can kind of see an example of a vignette here. We have Loretta, who was, a 39-year-old female with a history of X, Y, and Z. And then for each patient, participants basically had to think aloud while selecting a treatment strategy for the next 4 hours in terms of deciding how much IV fluids they should give them, how much vasopressors they should give them, which again are typically the most common treatments for sepsis in the ICU. And so we created 4 different visualization conditions by replacing basically that right half of the tool that I just showed you with either no AI at all, or one condition was just text only. So basically the straight up recommendation of what the AI tool suggested, give this treatment at this dose, et cetera, et cetera. Or there was a feature explanation condition, which would basically give them some information about what features about the patient were responsible for this prediction. So for example, in this example, the glucose bar is really long. So the fact that this patient's glucose levels are maybe a bit strange, maybe that's leading them to predict the treatments it's doing. And then finally, there was a 4th condition, which called alternative treatments, which is basically showing you what are the top treatments at the top 5 treatments that the AI recommends, and then they're color coded according to how frequently doctors in the past would have done this treatment for this type of patient. They're kind of giving you some evidence about what else is out there, and how often is it done in practice. So I'm just going to talk about some key results of the study. But if we think about kind of the perception of AI guided decisions, we first asked participants basically, how did AI affect their confidence And they noticed that the feature explanation chart really made them significantly more confident than the text-only condition, and slightly more, but not significantly, than the alternative treatments charts. So it appears when you provide some exploratory or explanatory information to clinicians, they find the AI kind of more helpful and confidence-inducing. However, if we look at the reliance on AI, how did this actually affect the decision-making process? You can maybe see here that there were really no significant differences in levels of the concordance with AI. So this was maybe, the bad news for AI, right? It didn't move the needle. Although the visualization condition certainly affected participants' perceptions of the tool, they didn't seem to affect whether they ultimately agreed with AI. So what factors did affect whether they went with AI or not? To find that out, we really had to conduct a qualitative analysis of these think aloud transcripts, basically for every AI-assisted decision that we observed. Because we noticed when we were actually doing the experiment, people were behaving very differently. So we were kind of surprised to see, no differences here across conditions. And again, this was, random order. We showed them in random orders. We also gave them random patients for each condition, and there was no kind of explanation for that. So again, we went to the transcripts of the data when they're thinking aloud, and we basically saw that there were basically 4 different types of groups of people. First, there was this kind of group of, ignore, we called them, where basically they just kind of, whatever the AI said, they didn't care. They didn't do anything with it. The recommendation of the AI didn't factor in decision making at all. They would look at the AI decision, but they would often kind of evaluate it relative to what their own judgment was. So, for example, in this particular quote, okay, this patient might be hypervolemic, but certainly I wouldn't start a vasopressor on this patient, and an IV fluids at this dose over the next 4 hours. I disagree with that as well. So they were basically kind of taking the AI, comparing it to what they were already going to do, ignoring the AI, but just kind of seeing how the AI was different or not. So they were really just kind of evaluating the tool, and kind of, but not actually taking any of the AI recommendations into their final decisions. One of the more interesting groups, though, was this group of kind of that we call the negotiate group, where participants would sometimes, prioritize certain aspects of the recommendation to follow, but then deferred others to their own intuition. So, for instance, one participant responded to this recommendation, well, I don't necessarily disagree, but I probably wouldn't start with the fluids, but then I would escalate to vasopressors if there was no response. So again, they kind of adapted the timing of the recommendation to their own assessment. And so they kind of wanted to kind of be able to kind of take certain parts of the AI recommendation and then adapt it to what they thought was best for their patient. Um, um, and and so, and then there were also a few people that trusted the AI no matter what we said. They would do that too, but I'll kind of move on from there. So what was interesting is that, clinicians really expected the AI to kind of replicate standard care practices, such as administering fluids before vasopressors. This is something that they were taught during their training in medical school and beyond, where basically always give fluids before vasopressors. Even though if you look at current up-to-date medical literature, sometimes they say actually doing both at the same time actually helps. So even though the AI was sometimes recommending things that were kind of now being promoted in the latest literature, because it didn't reflect to the standard care practice that they were used to, they often wouldn't kind of listen to it. And they also kind of really remarked that kind of rigorous and credible AI validation is really required for trust. So again, if there was kind of a study in some famous medical journal that said that this tool improved outcomes, then I would say it'd be kind of useful. But until then, I'm going to kind of be a little skeptical. And I think that that's given such the importance of decisions like this, that probably makes a lot of sense. So anyways, there's some thoughts there. So okay, so let me just so I talked about 3 kind of different. Oh, so let me just talk about some implications of this then, I guess. Is really thinking about, okay, we initially kind of approached the study aiming to design for the type of human AI reliance that's often described in literature, where the decision maker kind of either accepts or overrides a recommendation based on how likely they think they are to kind of err compared to the model. But this negotiation pattern that we observed is kind of an interesting lens to kind of understand how users allow the AI to influence them. Basically, supporting a more effective negotiation of the AI, both when and across individual decisions, could be one way more to promote more appropriate acceptance of predictions. But right now, of course, AI isn't really formulated to participate in a negotiation. So future models would really need to work to support this kind of to basically dynamically adjust to what aspects of the recommendations they present to users. And then how you evaluate these negotiation behaviors is a whole other challenge. But some of our current ongoing work is going to really look at that. How can we better support this kind of interactiveness with the AI to give the user what they want and what they feel comfortable with. Um, okay, so kind of uh, and again, one of our original plans was actually to kind of scale up the study and deploy the system more broadly in the point of care. Actually, our colleagues at a major hospital that we work with were really excited to do this. But we noticed that so many strange behaviors that this AI model was doing during this user study that we didn't really feel comfortable. So basically, when we started looking at our tool with Zeno and AutoProfiler, we were like, oh, wait, this is maybe it's doing some things that don't make much sense. So, and again, in fact, when we explored some of the choices that the model developers made that built this model, when it came to some things like what are the, how do they bin dosage amounts of the treatments, and other small decisions like that, it really made clear that their assumptions made the recommendation sometimes quite bizarre and sometimes clinically unrealistic as well. So this made us take a step back and actually worked on bringing domain experts into the loop during the modeling process. And so some of Venkat's earlier work here, I'm not going to have a chance to go too deeply, but really tries to kind of build interactions and visualizations that allow domain experts that are not AI experts to be part of the modeling process so they can maybe catch these poor assumptions or poor behaviors faster. Um, we've often heard so many stories of the model development process taking, 3 to 6 months with experts in the loop. And then finally, when it's deployed, it's sometimes too late for the experts to fix. So I'm really excited about this work, and I think there's a lot to do in this space. Okay, but with that said, given that we're already 50 minutes in, I guess maybe I'll say that I have some closing thoughts that I think in order to understand human AI decision making, we really need to go beyond studies of whether decision makers kind of either accept or override a recommendation, um, and really force them to build a mental model of the AI on their own. Instead, I think we need better tools to kind of understand the behaviors of AI models and be upfront with the decision makers about what those behaviors are. So some of our work is on the path to supporting this, but I think there's still a long way to go, particularly with more complex models out there. Um, but that's kind of why we're excited to do research, right? So again, I want to thank Alex, Will, Venkat, and Caitlin for spearheading all of this work. And I'll just again say if any of this work is interesting to you, you can feel free to learn more about it on our labs webpage, dig.cmu.edu. So with that, I think maybe I'll pause now and see if you have any questions.
I already can see some hands up, Adam. Francisco, please go ahead. You can.
Thank you, Professor Augusto. Hi, Adam. It's always great to follow your work, as usual. So I have a question regarding Zeno framework. I have a lot of questions, but I'm going towards the most critical for me right now. So we are working with Zeno, and as you presented in your presentation, Zeno is a great tool to understand behavior of a classifier for a specific, let's say, unbalanced situation of the data set. And we start using that with the project that we have that relates with medical imaging, breast cancer, where we have a classifier for the severity classification of the of breast cancer. So in radiology they use a scale from 1 to 5 called BI-RADS. And the tool was great to understand the imbalance of the data set. So for instance, understand that the a BI-RADS of 3 is missing a lot from the data sets. However, we are also trying to use different classifiers, such as, okay, if we have, for instance, a BI-RADS of 3, or for instance, like you said, the breast density, what is the correspondent explainability variables that are going to explain that specific classifier? but these variables are coming from, in our case, are coming from different classifiers. And one challenge that we are facing is trying to bring more classifiers together to Zeno. And I would like to ask if you think about that already. How would you suggest to deal with challenge? And if you have any recommendation with that, it would be great.
Sure. Yeah. Thank you for the question again. I'm happy to also chat offline. Since you have a very specific question, which sounds really interesting, would be happy to kind of learn more and help. But yeah, in general, again, the goal of Zeno was really to be this framework where you can bring in lots of different types of classifiers or metadata that you can get from different classifiers and bring it all together in one place where we can see the relationship between them. So in theory, Zeno was really designed for exactly that, to kind of see where are the subgroups that kind of map for these different types of things. And so, yeah, I'd be happy to kind of meet offline and talk about it, how that's working well for you or not, learning more from you about that, and that could maybe influence future work. But it's great to hear that you're actually using Zeno. That's kind of a really fun to hear. And the goal is really to kind of let you kind of compare different models and see performance and see how different subgroups work differently across them. So yeah, we'd be happy to chat more offline if you'd like to go into more
Sure.
detail.
I was expecting to evolve you in another student, but let me just have the results so that don't waste your precious time. And right now, so me and Adam, we are sharing a student from IST, Vicente Sobral. So we are also finishing that work. But then it will going to be really useful also to work on Zeno, because one of our main concerns is trying to not only increase the quantity of the data sets we have for breast cancer, but also the quality. So how much information can we have for the same image? And to understand what are the priorities, Zeno is like one of a kind tool for that. So that's really great. And thank you so much for the great work that you are doing with your students. It's really an inspiration for me.
Thank you very much. That's very kind.
Thank you, Francisco. Anyone wants to ask a question while we have Adam here? If you don't mind, Adam, while people are gathering their courage to ask. I was just curious. So this is not directly on my area of research, but I was quite curious when you were discussing sort of the feedback from the doctors, or the way they sort of the way you cluster the doctors into these sort of different profiles, the way they I wonder, even the ones they ignored the instructions, do you have some insights into, did it make them question their own, so did they make them reflect on that? So did they ignore it, but actually has a positive effect? They thought a bit more about sort of what they would recommend. I don't know if you have some more words on that.
Yeah. So basically, the way the study worked is we kind of had them make a decision before we showed them the AI recommendation, and then could decide to change it or not after that. And then again, we had them kind of think aloud the decision-making process to kind of understand that. And so yeah, so certainly for the ones that ignored it, it would often sometimes make them think a little deeper about it. And again, they would sometimes compare, okay, what am I doing versus the AI, and why am I doing it that way? And they try to even, oftentimes would kind of justify that out loud during that think aloud process. And so I think that's an interesting thing to think about too, is what is that interaction useful? Like, as in, does it help them kind of give it their decision a sanity check, or does it slow them down and kind of prevent them from thinking, or all these different types of things? And so I think what we're really trying to understand is how can we better uh, think about ways that we situate the AI to present things in ways that can hopefully get them to reflect on the process without, necessarily, causing some negative behavior associated with that too. And so we're really trying to also think about, how do we design, when do we present the AI also? Like, uh, when do we want to show them something? Should we only show them something if, we think they're really wrong and save those things, or we give them an alert every time giving our things, and then they pretty ignore them and stuff. And so I think there's a lot of interesting work to be done about exactly how these the best way to kind of share these decisions are. But yeah, but in general, yeah, again, in the study, at least people were not like, not even reading them. But I guess you could imagine this was, could maybe basically also somewhat be attributed to kind of a novelty effect. Like they were seeing these recommendations for the first time, so they all kind of thought they were kind of interesting. And so again, one of our next steps is to actually kind of do a longitudinal data study of how if they got these recommendations, you know, every day for a long time, again, how would their behaviors change in that case too? And so that's kind of we're excited to kind of learn about that.
I'm gonna let Noah ask a question, but before that, I just want to do a quick follow-up, and I guess it's a bit of a provocation, Adam. Because for this particular population, I'm quite interested in this group that's the. I wonder if actually providing them with wrong or with provocative recommendations, would that elicit a better. At the end of the day, the patient just wants the best care, right? And would actually have an AI that provokes and has actually provide some mistakes here and there for the doctor to pick up on and just would that be an interesting yeah, sort of a bit.
Yeah. Yeah, no, it's a really interesting idea. And yeah, giving them quote unquote bad advice just to kind of make them think through the process, I think is interesting. Of course, you wouldn't want them to then actually follow the bad advice. So how would you exactly? So there's a lot of interesting research to be done about what is the most effective way for people to think critically with AI. And I think that's still a big open question right now. Yeah.
Noah, do you want to ask a question?
Yes, I actually do have a question regarding the same area that Augusto just mentioned, which is basically, have you considered testing the same idea in different cultures? Because I don't know much about the topic. This is not my area of expertise at all. But for instance, I remember in the Netherlands that they just for basic like consultants, they had something like Google where they really depended on technology. So maybe if you tested somewhere else, they would have a different response, maybe.
Yeah, we haven't done that work ourselves. There have been a lot of work looking at kind of how different cultures appreciate or do not appreciate kind of AI and technology broadly. I haven't seen any studies, too many studies with that directly related to healthcare, but I think that is a really, at least anecdotally, we see a big differences about how people are kind of willing to defer trust to technology or not. And so I think that is an interesting thing to think about as these technologies get deployed across different styles. I mean, all of our study was within one institution and one hospital in one city, so it's kind of limited now to kind of control for that effect. But I think going forward, looking at those differences, especially before we deploy things broadly, I think that's really, really important to do. And so, yeah, so I haven't done particular work in that space myself, but I do think that's a valuable research question to ask, especially before things go further. So yeah, it's a really good, and I think that would be really interesting to see, not even just how do they trust or not, but again, yeah, are these interactions differently, right? Are they more trusting? Are they more ignoring? Or are there even some new categories of people that we didn't see in our study because there's, different cultural norms, different places. So yeah, it's a really great question. I don't have a good answer for it, but I think that's definitely worthy of future research. Thank you.
Thank
Okay,
you.
thank you. No, it's 7 p.m. or I think believe 2 p.m. where Adam is, maybe 1 p.m. So I think it was right on time to wrap this up. It's always underwhelming when we wrap these Zoom sessions, but I really want to thank Adam for his time and thank you, Adam. Everyone has your contact if they want to reach you for any
Yep.
further questions. And